Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. Tonight we are going to continue with our discussion on aqueous ionic equilibrium that we started a week ago. So I present to you Aqueous Ionic Equilibrium Volume 2. As always, your feedback is more than welcome and highly encouraged. So if you're watching this live, please feel free to drop your thoughts in the chat. And if you're watching this as a video, please leave me a comment. Without your feedback, I am lost. I would also like to add that by the time I'm done streaming and recording and uploading this as a video, I'm going to have a playlist entitled Aqueous Ionic Equilibrium Live Streams. As of this moment, right now, I don't have one yet because I've done Volume 1 just a week ago, and now we're doing Volume 2. So after this, there will be 2 videos. So I'll combine those into a playlist called Aqueous Ionic Equilibrium Live Stream. So later on, if you're watching this as a video, there will be a link in the description. All right, so we're going to go ahead and get started, and we're going to start by discussing the material from Volume 1 that we covered a week ago. So what did we talk about? Well, it's not shown on the PowerPoint here, but the first thing that I talked about was kind of a disclaimer about acids and bases and how you really have to understand acids and bases in order to understand aqueous ionic equilibrium. There's just no way you can get away from that. So if you're not super confident in your understanding of acids and bases, then I highly suggest that you check out my acids and bases live streams playlist. There's a link down there to it in the description. It has everything you need to know, all of that prerequisite knowledge that's necessary to understand the content of this topic, aqueous ionic equilibrium. Okay, so already got a message from Kitty B. Says, hey, hello again. Hey, welcome back. Thank you for being here. That goes to everybody in the stream. Thank you for being here. Appreciate it. So what did we talk about? What did we talk about? Well, we talked about how the topic of aqueous ionic equilibrium can be thought of as divided into 3 subtopics, if you will: buffers, titrations, and solubility equilibria. And so we began our discussion by talking about buffers. What is a buffer? What does a buffer do? Of course, the definition of a buffer is simply an aqueous solution that contains significant amounts of both a weak acid and its conjugate base. The function of buffers, what they do is they resist changes in pH. So we're going to talk even more about how they do that. So basically what they do is if you add an acid to a buffer, then that acid will get consumed by the weak base that's in the buffer. If you add a base to a buffer, then the added base will get consumed by the weak acid that's already in the buffer. And so that's how they do it. We're going to talk about that in more detail in just a moment. We talked about how to calculate pH of a buffer solution. We looked at something called the common ion effect, which is basically what happens when you already have some weak base in the presence of, you already have some conjugate base in the presence of a solution with a weak acid, right? If you already have some of that conjugate base in there, then the ionization of that weak acid is going to be suppressed relative to a solution that didn't have any conjugate base in there in the begin with, right? And it's called the common ion effect because if you have both a weak acid and its conjugate base, then they share a common anion. So that's the common ion effect. And then we also talked about the Henderson-Hasselbalch equation, which is a very, very convenient alternative to the equilibrium approach to calculating pH of a weak acid or pH of a weak base type of problems. And so that equation is shown here in this green box where you have the pH is equal to the pKa plus the logarithm of the concentration of your base divided by the concentration of your acid. So instead of doing that whole equilibrium thing with the ice table and all that stuff, the quadratic, you don't have to do any of that. You can just plug the numbers that you have into this Henderson-Hasselbalch equation and calculate pH very, very quickly. Of course, the Henderson-Hasselbalch equation is convenient, but it only works when the x is small approximation is valid, which basically means that you have a reasonably low value of Ka and a reasonably high value of your initial concentration of your weak acid. So that was all of the Volume 1 material. So what are we going to talk about tonight? Well, tonight we are going to talk about, and I'm going to move myself out of the way here, we are going to talk about pH changes in buffer solutions. So pH changes in buffer solutions. What does that mean? Well, if you add an acid or a base to a buffer, how does that buffer respond to that disturbance? So that's what we're talking about. We're going to talk about how to calculate the pH upon adding an acid or a base to a buffer. So we need to understand how buffers respond to the disturbance that is the addition of an acid or a base. So let's talk about that. So imagine I have a beaker, and in that beaker I have an aqueous solution. Let's say I have a 1 liter solution in which I have a 0.5 molar concentration of both a weak acid HA and its conjugate base A minus. Okay, so I have this buffer here. I have 1 liter of this buffer, 0.5 molar HA, 0.5 molar A minus. Now, using the knowledge that we learned a week ago, we understand how to calculate the pH of this buffer solution, right? We can just simply take those concentrations along with the pKa for the acid, which we could look up in our textbook, or it'll just be given by the problem, and we can insert that into the Henderson-Hasselbalch equation to get the pH of that buffer solution. But what if I were to take some strong acid, such as this HCl, and add it to this buffer? Then what would the pH be? How do we calculate pH upon adding a strong acid to this type of buffer here? Well, in order to understand this, we need to understand what happens to that acid when it gets added. And in the next slide, we're going to take a look at that. So if I add, let's say, HCl, a strong acid, to this buffer here, what's going to happen is that acid that we add is going to get consumed. It's going to get neutralized by the weak base that's already in that buffer to produce more weak acid, right? So I add some acid that'll be consumed by the weak base that's already in there to produce more acid, okay? So in other words, the concentration of the weak acid is going to increase while the concentration of the weak base is going to decrease. So that's what's going on here, adding a strong acid to a buffer. So basically what's going on is this weak base that's already in the buffer is converting the strong acid into weak acid. And as long as the amount of HCl in this case is sufficiently small, then the resulting change in pH would be minimal. And so we're going to look at how to do that. So anytime you're calculating the pH change of a buffer solution, there are two parts to the calculation. There's the stoichiometry calculation, which is something that's new that we haven't seen before. And then there's the equilibrium calculation, which is something that we know how to do. And if you've been following along in these live stream presentations, you probably can do blindfolded because we've done it over and over and over again, right? So let's talk about this first part, this stoichiometry calculation. So basically, what I've done here is I've set up this table to track the addition of HCl. So I have the conditions before I add the HCl. I have what the addition is. In this case, I'm just going to say we add 0.1 moles of HCl. And then in this third row here, we have what remains after the HCl addition, right? So notice that this is not an ICE table. This is not initial change equilibrium. This is just a table that is helping us track the progress of the stoichiometry calculation associated with this problem. So before the addition, of course, we have our weak acid and our conjugate base, both with a concentration of 0.5 molar. And since the volume of the solution is 1 liter, that means we have 0.5 moles of each, right? Everybody still with me? If I have 0.5 molar and my total volume is 1 liter, then that means I have 0.5 moles, right? I think it makes sense. So again, this is just the chemical equation that represents the added acid being consumed by the weak base to produce more weak acid, right? And so before the addition, we have 0.5 mole of each. The addition, which I'm just saying is what we're adding, this isn't something that, this would be like something that's given by a problem, is 0.1 moles. And so what's going to happen is that 0.1 mole is going to be converted into the weak acid, right? So in other words, the amount of our weak base, the amount of our conjugate base, A minus in moles, is going to decrease, and the amount of our weak acid in moles is going to increase by the same amount. And that amount is the amount of strong acid that was added. So notice that after the addition, the concentration of our base has decreased by 0.1 molar, or 0.1 mole, right? It went from 0.5 moles to 0.4 moles, and then our weak acid has gone up from 0.5 moles to 0.6 moles. So again, basically the way it works is that the weak base takes that acid that's added to it and it converts it into the weak acid, right? And the reason why initially I have a concentration of approximately 0 molar here for H plus is because it's not exactly 0. There is going to be some H plus in that solution prior to the strong acid being added, but the amount that is present in the beginning is negligible compared to the amount that's added. So that's why it's approximately 0. So that is the stoichiometry calculation, right? And so now that we've done the stoichiometry calculation, we can move on to the equilibrium calculation. So the equilibrium calculation is pretty straightforward. Again, this is something that we've already done. We would just simply write the chemical equation associated with the ionization of a weak acid in water. HA plus H2O yields hydronium ion H3O plus and A minus. So, and then you can take one of two approaches to solve this problem, right? You can either use equilibrium approach, which we've done to death, or we could use the Henderson-Hasselbalch equation, which is my preferred method because I like to take the path of least resistance to solve these kind of problems. But notice that, so look at the initial concentrations of acid and base. They are 0.6 and 0.4 molar, right? So in the beginning, they were both 0.5, and then after that stoichiometry calculation where we tracked what happens when you added the strong acid to it, these are the new concentrations, if you will, of acid and base after that addition. And so these become the initial concentrations in your equilibrium problem. So let me just repeat that again. So the new concentrations from your stoichiometry calculation from adding your strong acid, they become, those new concentrations, they become the initial concentrations for your equilibrium calculation. And so, like I said, what I would do with this is I would just put them into the Henderson-Hasselbalch equation and calculate it that way. So we're going to do a couple of practice problems later. And if you are finding value in this stream, I would appreciate your support in the form of a thumbs up or super chat if you want to. So, all right, so we're going to move right on. So now let's talk about the sort of the opposite of adding a strong acid to a buffer. Let's talk about adding a strong base to a buffer. So buffers, it's basically going to work the same way. The same principles apply, but instead of adding acid that gets consumed by the weak base that's in the buffer, now we're adding base that's going to be consumed by the weak acid that's already in the buffer. And this is the chemical equation that sort of represents that process, where you have some hydroxide ion, that's your added base. You have the HA, the weak acid that's already in your buffer. It's going to produce water, and it's also going to produce the more of your base. And so in this situation, it's like the opposite of what happens when you add an acid. Now that we're adding a base, the base concentration, the weak base concentration is going to increase, and the weak acid concentration is going to decrease. So what would that look like in terms of stoichiometry calculation and equilibrium calculation? That would look something like this. Let me move myself out of the way here. Big old head's always getting in the way. So we would simply write out that equation associated with the added base being consumed by our weak acid. So that's the same chemical equation that we saw on the last slide. And we would set up that, not ICE table, but that stoichiometry table where we have before addition, after the addition. So before the addition, again, we have 0.5 moles of both our acid and our base. The addition, let's say, is 0.1 moles of hydroxide ion. That's going to react with 0.1 moles of our weak acid to produce more weak base. And so the amount of weak acid in moles has now decreased by 0.1. The amount of weak base has now increased by 0.1 moles. And now we have new amounts, new values that we can carry over to the equilibrium portion of the calculation. And so we would set up the same sort of equation where we have the ionization of a weak acid reacting in water, and we can either take the equilibrium approach or the Henderson-Hasselbalch equation, and these are our initial concentrations that have resulted from the addition of strong base. So that is basically what happens. That is how a buffer reacts. That is how a buffer responds to a disturbance in the acidity or alkalinity of the buffer caused by the addition of a strong acid or the addition of a strong base. And so now what we have left to do is we're going to do a couple of practice problems where we sort of put this knowledge to work and see sort of how it goes. So since we're doing practice problems, they are going to require the use of a scientific calculator. I've got mine right here. So if you would like to follow along, which I would definitely encourage, now would be the time to grab your scientific calculator because we're about to get started with some problems. So I'm going to take you guys to the whiteboard, and I've already got a problem pasted up here. It says to calculate the pH change upon adding 0.30 moles of hydrochloric acid to a 1 liter buffer solution containing hydrofluoric acid with a concentration of 1.40 molar and potassium fluoride with a concentration of 2.00 molar. And it also says that the Ka of HF is 6.3 times 10 to the minus 4, right? So we want to know the pH change. So I'm going to highlight that right here. So since we want to know the change in pH, we need to know both the pH in the beginning before the acid was added and the pH later after the HCl was added. And so let's start by calculating first the initial pH. So this is before we've even added the HCl. How would we calculate the pH of that buffer solution before the acid is added to it? Well, I think we could use the Henderson-Hasselbalch equation. So let's just call this pH initial. That sub I just means initial, right? The initial pH. What is that? Well, remember, the Henderson-Hasselbalch equation says that the pH is equal to the negative log of, well, let me back up here. pH is equal to pKa plus the logarithm of the concentration of base, I'll just call that A minus, divided by the concentration of the acid, right, which I'll call HA. So that's the formula for the Henderson-Hasselbalch equation. So all we need to do is just plug the values that we know into it to calculate that initial pH, right? And so pKa, well, it didn't give us pKa, but it gave us Ka. And so to get pKa, all we have to do is take the negative logarithm of our Ka. So it's negative log of 6.3 times 10 to the minus 4. So that'll give us our pKa, right? P anything is just negative log of that thing, right? And then we're going to add to that the logarithm of the concentration of base over concentration of acid. So concentration of base, according to the problem, that's going to be our potassium fluoride. That's 2.00 molar, so 2.00. And then for our acid, that's 1.40. And so I'm going to go ahead and plug that into my calculator real quick, and that'll give us our initial pH. So again, if anybody wants to follow along, I would encourage that, especially because it's entirely possible that I'll get a calculation wrong, and if that happens, I am more than happy to be corrected. So, okay, negative log of 6.3 times, 6.3 times 10 to the minus 4 plus the logarithm of, what is it, 2 divided by 1.4. Okay, the value that I got for the initial pH is, what did I get? I got 3.36. 3.36. So that is, again, all I've done here is just use the Henderson-Hasselbalch equation to calculate what the pH is in the beginning before we add the strong acid to it. So at this point, what I'm going to do is I'm just going to erase all this stuff because we are going to need the room later, and I'll just keep this initial pH is equal to 3.36. I'll just kind of keep that over here, nice and handy for when we need it. So now what we need to do, is figure out the new pH, right? The pH change, or the pH upon adding the hydrochloric acid. So let's write the equation for what happens when the HCl gets added, right? So the HCl, we don't really care about the Cl, we care about the H+. That's the acidic part of HCl, right? So the H+ that's added, right, that's going to react with what? That's going to react with the base, right? And in this case, the base is fluoride ion, right? The potassium ion doesn't really do anything, but you have to have it in the solution in order to have fluoride ion, or at least you have to have some cation balancing out that charge. So really the basic part of this, if you will, is the F-. So it's going to be H+ plus F-. And I'm leaving out the aqueous in parentheses just so I can save some space, but both of these are aqueous. So that's going to react to form HF, which is our weak base, right? And so we can simply do that that table, right? That sort of table where we had before the addition, we have what the addition is, and then we have after the addition. So we can use this to sort of track what's going on here. So before the addition, H plus approximately 0, virtually nothing in there compared to how much we're about to add, right? So F minus, what's that going to be? That's going to be 2.00 moles, 2.00 moles. Notice that I've written the word mole here, or the symbol for mole, not molar. That's very, very important. And I basically just did the calculation in my head where if I have 2 molar of something and the total volume is 1 liter, then that means I have 2 moles of something, right? So that's our initial amount of F minus. And then our initial amount of HF, excuse me, is 1.40 moles, right? So what is the addition? Well, we're not adding any F minus, we're not adding any HF, we're just adding H plus. So how much H plus are we adding? Well, according to the problem, that's 0.30 moles, right? And so what's going to happen is the amount of F minus is going to decrease by 0.30 moles, and the amount of HF is going to increase by 0.30 moles. And so after, we're going to have basically no H plus. It's going to be all neutralized by the weak base that's in that buffer, right? And so what do we get? So we get 2 times 0.3, so that would be 1.70 moles. That's our new amount of our F minus. And then for our HF, that's going to increase by 0.30 moles, so that's 1.70 moles, right? So afterwards, look at that. We have the same amount of base as we do acid. You know, when I wrote this problem, I didn't even consider that would happen. Like I just kind of wrote it out like I didn't actually solve the problem, but look at that. So the amounts of weak base and weak acid and conjugate base are the same. So now that we have these new amounts, which I'm going to highlight, right? 1.70, 1.70. So now we're going to take these and perform the equilibrium calculation. So the stoichiometry calculation is done. Now all we have to do is the equilibrium calculation, which basically means that we can just use the Henderson Hasselbalch equation once again with these new concentrations, and that'll get us there, right? So the pH, let's see, pH, I'll just give it a subscript of F, final, is equal to pKa, so that's negative log of Ka, so that's negative log of 6.3 times 10 to the minus 4, plus the logarithm of the concentration of base divided by concentration of acid. You can use the amount in moles. You don't necessarily have to use the concentrations, because like in this problem, we're basically assuming that the change in volume upon adding the HCl is negligible. So we're not really factoring that volume change in. In some cases, you might have to if the volume change is significant, but we're kind of making that approximation. Just wanted to put that out there. So now we have log of 1.70 over 1.70. 1.70 over 1.70, that is 1. And so it's really log of 1. And if you type log of 1 into your calculator, you will get 0, because 10 to the 0 power is equal to 1. So this whole term basically cancels out, right? So we get pH is actually just equal to pKa at this point. And so the pH, the final pH, is going to be simply this problem right here, this expression right here, negative log of 6.3 times 10 to the minus to the minus 4. Let me type that in my calculator real quick. Negative log of 6.3 times 10 to the minus 4. What is it? All this stuff. I got 3.20. 3.20. So I'm going to sort of start erasing some stuff here. So what we're going to do is we're going to sort of line these up, right? So we have our initial pH, which was 3.36. And now we have our final pH, which is 3.20. So our pH did go down, although it did go down by just a little bit. KDB says 3.20. Yes, that is absolutely correct. Thank you for your participating. Since you got the same answer, I'm pretty confident now that I didn't screw up somewhere. So 3.6 minus 3.20. So if I wanted to calculate the change, let's just call that, I don't know, delta pH. Delta pH, what would that be? That would be, final minus initial. So that's going to be what? Negative 0.16. So yeah, that is how you do this problem. And I just realized that my camera is in the way of this stoichiometry table. See, this is why I want people to participate in the chat. Because sometimes I just get lost in the problem and I'm not like making sure that, I'm not in the way of something. So that's a little embarrassing, but whatever. Hopefully you guys get the idea. Hopefully I was explaining it well enough throughout that you didn't even really need to see it. That's my hope, but anyway. All right, so what we're going to do is we're going to clear all of this information off the whiteboard. I got another problem for you. It's going to be a little bit long-winded, and you'll see why, because I'm going to sort of explain something in the middle of doing the problem. So there's going to be like a teachable moment sort of within the problem, if that makes sense. So, all right. I think I got the problem ready to go. And here it is. Okay, so this problem tells us to calculate the pH change upon adding 0.30 moles of sodium hydroxide, NaOH, to a 1 liter buffer solution containing ammonia with a concentration of 1.40 molar and ammonium chloride, NH4Cl, with a concentration of 2.00 molar. And it asks us and it tells us that the Kb of NH3, the Kb, the base dissociation constant, is 1.8 times 10 to the minus 5. So it's a similar problem to the one we did a moment ago, so the same principles are going to apply, but since we're dealing with a base and its conjugate acid, we have to do a little bit more thinking, a little bit more reasoning in order to solve this one. So far in this short playlist of 2 videos, or 1.5 videos, right? This one, I guess we're halfway through, so to speak. We've looked at buffers that have a weak acid in its conjugate base. In this case, however, we have a weak base, NH3, and its conjugate acid, which is NH4+. And so, and we're not given a Ka, we are given a Kb. And so we have to figure out how to somehow get Ka from Kb in order to apply the Henderson-Hasselbalch equation, right? So once again, I'm just going to write that Henderson-Hasselbalch equation so that we all are following along. So pH equals pKa plus the log of concentration of base over concentration of acid, right? pH is pKa plus log of concentration of base over concentration of acid. So again, the only way that this equation works is if we can find pKa somehow, but we're not given pKa, we're not even given Ka, but we are given a Kb. So that is basically where we are. We're kind of stuck, so to speak, but we're never stuck because we can figure out how to solve this. Okay, so what we need to do is we need to derive a relationship between Ka and Kb, or pKa and pKb more specifically. And so if we dig back into our memory banks when we were studying acids and bases, we learned one relationship that was very important, which is that the product of Ka and Kb is equal to Kw. Kw, that's the ion product constant for water. It carries a value of 1.0 times 10 to the minus 14 at 25 degrees Celsius. Ka times Kb is equal to Kw. I'm going to sort of lasso this to the middle, So what I'm going to do is I'm going to manipulate this equation a little bit, because I just love manipulating equations. I'm going to take the negative logarithm of both sides of this equation, right? So I'm going to take the negative logarithm of both sides of this equation. So left-hand side of the equation, what does that look like? Well, it's the negative logarithm of a product of terms, right? And whenever you have a logarithm of a product, that is going to be, let me write that down. So if you have the logarithm of a product, I'll call it a times b, then that is going to be equal to the sum of the logarithms for the individual factors inside the logarithm, right? So log of a times b is equal to log of a plus log of b, right? So I'm going to use that property of logarithms to my advantage to further manipulate this equation, right? So this equation can be rewritten as minus log of Ka plus the minus log of Kb is equal to minus log of Kw, right? Minus log of Ka plus minus log of Kb is equal to minus log of Kw. Now, these terms should look pretty familiar, right? What is minus log of Ka? Well, that's pKa, isn't it? Yeah. Minus log of Ka is nothing more than pKa. And minus log of Kb, what's that? Well, you guessed it, that's pKb. So we have pKa plus pKb is equal to minus log of Kw. Well, Kw is a constant. We know what it is, right? It's 1.0 times 10 to the minus 14. So really what we have is minus log of 1.0 times 10 to the minus 14, right? And if you do that, if you put that in your calculator, you probably don't even have to put it in a calculator because the numbers are these nice easy powers of 10, then you will get 14. So we have just derived a relationship between pKa and pKb. They add together to 14. pKa plus pKb is equal to 14. Okay? So now that we understand that relationship, I'm going to go ahead and, whoops. Here, I'm just going to erase some stuff here. Give me just a moment. I'll take this and drag it over there, right? pKa plus pKb is equal to 14, right? So again, now we have a way to go from pKb to pKa because that's what we need in order to be compatible with the Henderson-Hasselbalch equation to get pH, right? And so we know that the Kb is 1.8 times 10 to the minus 5, right? So that means that pKb is equal to the negative logarithm of 1.8 times 10 to the minus 5, right? So what is that? Negative log of 1.8 times 10 to the minus 5? I don't know what it is. I have not done this calculation ahead of time. I just kind of wrote this problem on the fly. So let me calculate that real quick. Negative log of 1.8 times 10 to the minus 5. I got 4.74. 4.74 for my pKb. Okay? And so, since the pKa and the pKb add up to 14, the pKa is simply going to be equal to 14 minus the pKb, which we just determined is 4.74, so 14 minus 4.74, and that is, I'm actually using my calculator, yes, because I'm terrible at mental math. I'll just admit it. 14 minus 4.74. Not only am I terrible at mental math, but I also don't want to humiliate myself on my own live stream. So 14 minus 4.74, pKa is going to be 9.26. pKa is equal to 9.26. So that is how to get pKa from pKb. It's understanding that relationship, the fact that they add to 14. I didn't want to just give you that formula. I wanted you guys to understand why that formula works. And you'll find if you watch any of my content that I very rarely start with an equation and just tell you to apply it. Like I try to explain the origin of that equation, the reasoning behind it, and why it works. Probably would be easier if I just gave you a formula and said get to work, but I don't know. I like to talk about why formulas work. All right, so with that in mind, we can now, we're in a pretty good position, so we can use the Henderson-Hasselbalch equation to get the pH initially, right? So what is the initial pH? Well, that's going to be pKa, which is 9.26, plus the log of concentration of base over concentration of acid. Concentration of base, that's NH3, so that's 1.40 molar. And then the concentration of acid, that's 2.00 molar, 2.00 molar. Got a message that says this is definitely going to help me retain the info rather than just memorizing and plugging in values. Yeah, I agree. I think the problem is a lot of people just don't like have any interest or desire in learning, which completely blows my mind. Why you wouldn't want to learn, like when you have the option to learn or not learn, like why would you just choose not to learn? I don't know, but I know a lot of students are like that. Anyway, so I'm just going to plug this into my calculator real quick to get the initial pH. So 9.26 plus the log of 1.4 over 2. Let me get that real quick. Okay, 9.26 plus the logarithm of 1.4 divided by 2. And the value that I got was 9.11. 9.11. So let me erase this stuff. And I'm not going to make the same mistake I made in the last problem where I accidentally cover up what I'm trying to show you guys. I won't let my webcam cover up what I'm trying to show you guys. I promise. You guys have my word on that. So, okay, we can erase that, right? Actually, no, let's not erase that. Let's keep that. Let's keep that pKa equals 9.26 because we're going to use that again later when we do the equilibrium part of the calculation. So I'm just going to take this. I'm going to stick it like up there. I think is probably a good spot for that. So, okay, I'm going to take that and just kind of, well, nope. Oh, never mind. Okay, I was trying to get too fancy. It wasn't working, so let's move on. So now we're in a position where we can set up the table that helps us track the stoichiometry calculation when we add the weak base, or when we add the strong base in this case. So let's start by writing the equation. So the equation is going to be OH minus, right? That's our added base. It's going to react with the weak acid that's in this buffer. So the weak acid is going to be NH4 plus. That's the ammonium ion that comes with the NH4Cl. The Cl minus doesn't do anything. It's highly inert. It doesn't contribute to the pH at all. Just chilling there. And that's going to react to form water and NH3, right? NH3. Okay, so this is just the acid that we add gets consumed by our weak, the base that's added gets consumed by our weak acid to produce more weak base. Okay, so I'll do the three sort of rows where we have before the addition, where we have the addition, and then we have the after the addition, right? So initially we have approximately 0 moles of hydroxides. Yes, we do have some in there, but they're negligible compared to the amount that we're going to add. NH4 plus, that's our weak acid, right? That's 1.40 molar given by the problem, or 1.40 moles, right? NH3, what is that going to be? That's 2.00 moles. As for the addition, well, the problem tells us that we add 0.30 moles of base, so the addition is going to be 0.30 moles of base. So we're not adding any additional weak acid or weak base to this. So basically what's going to happen is the concentration or the amount in moles of our acid is going to drop. It's going to decrease by 0.30 moles, so 1.40 minus 0.30. What is that? So that would be 1.10 moles, right? It's 1.10 moles. And then this one up here, the NH3 is going to increase by 0.30 moles. So 2 plus 0.3, that's 2.30 moles. And I'm very, very close to be to covering up this stuff, but not quite. Okay, cool. Still in the clear. All right, so now that we have our new amounts of weak acid and conjugate base that have resulted from adding our strong base to this buffer, now we can use these with our Henderson Hasselbalch equation to get the pH once again. Or if we wanted to, we could take the equilibrium approach and do everything with the ice table and all that. But I'm too lazy to do all that, so I'm just going to use the Henderson Hasselbalch equation, and I'm going to just assume that the X's small approximation is valid. So, okay, so now we're in a position where we can get, what is it? I'll call it pH final. I think that's what I did last time. That's going to be equal to pKa, which we calculated previously is 9.26, plus the logarithm of concentration of base over concentration of acid. So the amount of base in moles, that's 2.30. The amount of acid in moles, that's 1.10. And so this is our formula to get the final pH of the solution. So I'm going to type this in my calculator. I invite anybody else who wants to do the same. And leave me your feedback if I'm working too fast and blowing you in the dust, or if I'm going too slow and I need to speed things up. Like, let me know. I can handle the criticism, believe me. So, all right, 9.26 plus log of 2.3 over 1.1. And let's see. The value that I got was 9.58. And Kitty, who is our only participant in the chat, shame on everybody else who's not participating. I'm just kidding. The fact that you're here, I do appreciate, although it would be nice to have more people participating in the chat. All right, so yeah, I got 9.58. Kitty got the same answer. Cool. Looks like we are both correct. The fact that we got the same thing gives me a little bit more confidence that I didn't screw anything up. So I'm going to delete some stuff. Come on, there we go. So pH final is equal to 9.58. And I'm going to take that and just sort of drag it up here. There we go. So we have our initial pH, that was 9.11. We have our final pH, that's 9.58. So what would delta pH be? It would be final minus initial, so 9.58 minus 9.11. And so that would be 0. What? It would be 0.47. Am I calculating that right? I think so. Yeah, 0.47. So 9.58 minus 9.11. So, okay, guys, those are just a couple of problems. I know that one was a little bit long-winded, but it was long-winded for a reason. I wanted you guys to be able to have those tools in your pocket to be able to go from like pKa to pKb, and not just have those tools in the sense of like having formulas, but like, we've all had that moment where we've like forgotten a formula, and then you think, man, is there any way I can sort of logic my way out of this? Is there any way I can sort of reason and try to derive the formula even though I don't know it by heart right away? And yes, there is. So we just saw that in the example where we have a concentration of a weak base and its conjugate acid. So let's see. So that is it, everybody. Thank you very, very much for watching. Really, really happy to have you all here. We're going to keep this going. I was thinking next weekend, so what would the date be? That would be Sunday, August 22nd. I think I might do some kind of back to school type thing. I don't know. If you're watching this as a video, then it doesn't really matter. It probably already happened. But yeah, so that's going to do it for the educational part of this live stream. I hope you've all had a wonderful weekend, and I hope you are all geared up to have an amazing, wonderful, productive, awesome week this week. And all right, take it easy.